Hello, everyone, and welcome to today's episode of Sadlier School Live. My name is Camberly Woods, and I'm pleased to be bringing back Dr. Christopher, aka Chris Brunell. Thank you for being back, Chris.
My pleasure, Cam. I appreciate you bringing me in. Hope everybody's having a great day, staying safe today.
Yes, and I'm excited for today's topic because I have fallen in love with all of the pattern sniffing we've been doing here on Sadlier School Live. It seems like a fun game and a fun way to approach mathematics. And I'm excited that we're going to be doing some more pattern sniffing here on today's episode. And I just want to remind those viewers who are watching us live or maybe catching the replay of two things. One, we love to connect with all of you guys, so feel free to say hello to us in the chat. We'd love to connect with you and say hello back. And two, any of the resources that we shared today that have links, we will be dropping into the comments here on Facebook as well, so you can access any of those resources in the chat here on Facebook Live. So Christopher, I'm gonna go ahead and hand it over to you, or Chris, trying to be more informal here. We're on a Chris basis now.
Is that okay? I mean, it's fine with me.
I'm going to pass it over to you, and we can go ahead and pull up your presentation and dive into the topic.
Okay, let me quickly get there and start it off. Hopefully, it's now displaying, and I don't shut it off.
Great.
And now, if I can make it actually present. Hey, yeah, there we go.
There we go.
So yeah, we're in part 2 of pattern sniffing. Thanks for joining, and thanks Cam and everybody at Sadlier School for inviting me to come and play along. I'd like to first start off by referencing something I know Dr. Matthew has put together in the past and shown you and talked about, is the ideas from George Polya, and we both have a favorite quote of his that we probably learned somewhere in our undergraduate studies of math. It's better to solve one problem 5 ways than to solve 5 problems one way. And so I'd like to kind of think along those lines further today. Cam, did you have a link you wanted to share about that?
I just wanted to mention, in terms of this topic, solving problems multiple ways, you're right. This is something that Dr. Matthew Bayronovan has spoken on for Sadlier School several times. And I'm going to drop links to his on-demand masterclass or on-demand webinar on this exact topic. So if you're interested in checking out that training, you can access it in the link in the comments here.
Excellent. That's wonderful. Thanks for doing that. He does a wonderful job of that, I know. So it's great that you have that depth of resource to play with. Today, I'd like to just sort of pick up where we left off yesterday with this idea of patterns within numbers and sums of numbers. I want to say this, that there was while Polya is a famous and dear personality in mathematics education to me, I've read many of his books, How to Solve It, and other great books, which I would recommend anybody who's interested in teaching math or working with their own children. The book How to Solve It by George Polya, published in the either 50s or 60s last century, is still a great book, and it's easy to read for anyone, and I would recommend that. But Polya is not the first to advocate the idea of thinking about problems in multiple ways, and for that we really have to kind of go back to a guy named Pythagoras, who was a Greek mathematician of about the 4th century BCE, and he kind of got the Greek school of philosophy and mathematics going I'm not going to spend a lot of time on him, but just to say most people are familiar with his famous theorem, and we're not going to go there too much, but let's talk about this problem yesterday. You remember this, Cam? We were looking at how do you generate square numbers?
Yep, I do remember this.
Yeah, so we thought about the numbers 1 and 4 and 9 and 16
Uh-huh.
and so on. And it was we refer to them all the time as the square numbers. And my question to you is, why are they called the square numbers? What do you think?
Yeah, well, looking at the pattern I'm seeing here, when we look at the square of 2, so that line where we have the bright neon green.
This one right here?
Yep. If we lay out the 2 by 2, that actually creates a pattern of a square, or a 3 by 3 makes that periwinkle bluish color, and then the 4 by 4 making more of that maroonish burgundy color.
Yeah. And so if you're seeing all of the colors up into the all the colored squares up and to the left from the color that you're talking about. Is that right?
Yep, exactly.
You're talking about this sort of deep maroon, purple. Colors and I don't necessarily go together, so I'm going to trust you on that color. All I know is it's different from the other ones for sure. And I think this one's orange, right? And so everything from the orange up and left adds up to the number 25. Is that correct?
Yep, exactly.
And it's bordered by a 5 by 5 orange triangle, or orange collection, not triangle, but orange sets of numbers, right?
Yep.
This border. And so often we think, we talk to kids and we use language with students that we don't necessarily explain. I've run into so many students who say, well, 2 squared is 4 and 5 squared is 25, but they don't, and they see the little 2 that we write as an exponent up above the number, and sometimes x squared when they get to algebra. They wonder why, they may not really think about why why we call it a square. And the truth of the matter is it comes from these square arrangements. And for that, we definitely need to thank Pythagoras, because Pythagoras did a lot of work in what is called figurate numbers. And he designed these problems using rocks, pebbles in and on a sand table. So he just would lecture to people by putting rocks and pebbles in little arrangements, which is kind of interesting. If you know a thing or two about Greek, there's the idea of a rock, or one word for a rock is a calculi or a calculus. It's like sometimes if you go to your dentist, they talk about the stuff that builds up on your teeth as calculus.
Yeah.
But really, calculus is a Greek word for rock, and calculus ultimately becomes a method of counting or representing numbers to the Greeks, and it ends up in our modern mathematics under the name calculus, which is some people are familiar with. So, so thinking about the squares, that just real quick, and to get at this idea one last time, wouldn't you, if you look at this, you say, if I add 1 to 3, I get 4, which gives me that 2 by 2. And if I add 1 to 3 and to 5, which is the number of these purple ones, that gives me 9. And 1, 3, 5, 1 plus 3 plus 5 plus 7 gives me this 16, this square of 16. So this was in fact one of Pythagoras's early proofs of the idea that if you add up consecutive odd numbers, which we were talking about yesterday after looking a little bit at the patterns, if you add up those consecutive odd numbers, you get you always get a square.
So
And
interesting.
isn't that interesting?
Yeah.
It's so playful. He just, you know, he was just playing with these things and arranging them in various arrangements that was like, hey, if he had his iPhone with him, he might have snapped an Instagram of it and sent it off to the world. But instead, he talked to his students about it. Along those lines, I'd like to look at another color pattern just to push this a little bit further, and that'll be the end of the day.
Yeah.
And let's look at this. So Cam, looking at these color squares,
Yep.
what shape do the color squares sort of make you think of?
Yeah, well, based on how all of the different colors are arranged here on this graph, they're actually forming a triangle is what stands out to me is this.
Yeah, doesn't it look kind of like a triangle? I mean, if you ignore the jaggedy edge, right?
Yep.
And you just sort of abstract out and just sort of, you know, picture the colored region, it's sort of triangular. And is it true that if you stop, say, even here at row 3, doesn't everything above that also look like a triangle?
Yeah, it does. If you just stop it at certain lines and move like on the teal, yellow, and red and isolate those, it looks like a smaller triangle.
Yeah, so Pythagoras looked at these, and guess what numbers he called these?
These are his triangle numbers.
These are his triangle numbers. Now, which numbers are those? Whoops. I have unfortunately lost my slides.
Slideshow. Can restart it.
Ah! I'm going to stop sharing while I find it, if that's
Okay.
all right with you.
Yeah, no problem.
So what numbers do you think those were that what numbers were the triangle numbers that Pythagoras was talking about?
So I noticed that there was in the upper left-hand corner, I think we had a yellow, and so that represented 1. And then on the next line, we added 2 more, so we had 3. 1, 2, 3, and then we add another 3 with row 3, so that's 6. And then we add another 4, that's 10.
Yeah, so the numbers that he called the triangular numbers were those individual sums that you were just talking about, the 1, 3, 6, 10, and he looked at those and tried to extend that pattern. Is there something that you could look at in those patterns to generate more another pattern and other patterns that go with it?
Well, we could probably start to add up or look at the differences between the 1 and the 3, and then what's the difference between 3 and 6 and 6 and 10, and start to write down those numbers and see, hey, do we have any patterns in that?
You know, I love the fact that you just brought up look at the differences, because you say that choice that you just made to think about that is a very mathematician sort of thing to do. Well done. I just want to say, Cam, that was super mathematical of you. I think the more often we get students to think about and go and approach patterns by first looking at differences or some other kind of relationship, then we're well on our way to helping them become real pattern sniffers.
I love
And
it.
and I think you did that perfectly. Thank you very much.
Well, thank you. And I have loved these pattern resources you have shared with us the last 2 days that are great ways to open up this pattern sniffing dialogue with your students. Do you have any resources you could share with us as to where you go to find the patterns? Do you start by like looking at a topic like, hey, we're going to be learning about square numbers, and you work backwards into what patterns can I find to support teaching students about square numbers? How do you go about finding patterns?
So for number patterns like the square number pattern and the triangular number pattern, those are really out there. I mean, and widely available. So
Yep.
any simple Google search for square number pattern, triangular number pattern, and you will find oodles of resources for those.
Okay.
And there, what I did to create those patterns was I just used a spreadsheet and colored them. But what I did before we all had to do everything electronically was I used tiles, spare tiles, or pennies. In fact, pennies are great. Pennies are the best counter available. They're cheaper than any counter you would buy.
Yep.
And so there's just a lot of things you can do by arranging things in these successively growing arrangements.
Yeah. And I mean, I guess you're right. We could always go back and find rocks from nature and use those. That's all we have.
It worked for Pythagoras, and he did a lot. So
yep.
He literally, from what we understand, he worked with rocks on sand and a stick and a piece of string. Those were his tools.
Yeah.
And his mind.
And his mind. I love it. Well, thanks for being here with us today, and thanks for providing this insight. It has been really wonderful to hear your perspective on this. And it's just a fun way to approach math, again, to make it more meaningful for the students. And it really helps open up this dialogue so that we can help them develop this deeper understanding and make it fun at the same time. So
that's my hope.
Yep. Yeah, it is. So we appreciate you being here, and I will drop into the chat on Facebook as well a link to your Twitter so that if people want to connect with you over there, they can, Chris. And you will be back next week with us, but I will be back on here tomorrow at 3 o'clock p.m. Eastern, 12 o'clock Pacific, and we hope to see you there. Thanks again, Chris.
My pleasure. Thank you.
Talk to you soon. Bye.
Bye-bye.